Welcome to Deeksha Vedantu YouTube channel. I hope you all are doing great. I'm Aditi, your very own physics teacher, and at Deeksha Vedantu we are starting rapid revisions. Today we are going to study the rapid revision of magnetic effects of electric current, a very important chapter for your boards, for your pre-boards. This rapid revision will be very important since your boards, pre-boards are coming, and if you revise the whole chapter and you need a quick revision for your concepts, for a bit of numericals, for diagrams, anything, this lecture has got you covered. I have got you covered. So worry not and watch this lecture till the end. Do not skip. We are going to study this in a quick 25 minutes, I hope. Okay, so the outline will be basic. We'll study magnet and its poles, magnetic field, field lines, magnetic field due to different kind of conductors, straight wire, circular loop, solenoid, and some right hand thumb rule, Fleming left hand thumb rule, electromagnets, yada. Oops. Okay, so let's start. So in this chapter there is a very important person named Hans Christian Ørsted. One day he was doing an experiment with some current and his circuits, and there was a compass near all the circuits, and he realized that whenever he is turning on the current, he is getting a deflection in his compass needle, and compass needle gets deflected only due to magnetic field. So what is happening? Is electric current a magnet now? Is electric current producing some magnetic field? What is exactly happening? The same, he accidentally discovered that a compass needle gets deflected. So what is happening is, this experiment says that when there is a change in current, motion of electrons or charges, current is produced. When the current is produced, magnetic field also gets produced with it, hence proving that electricity and magnetism are related phenomena. And this research helped us in creating so many technologies like radio, television, and fiber optics, through which our internet reaches our home and everything else. So let's study about what magnet and its poles are. We know magnet is just an object that attracts certain materials like iron, nickel, cobalt due to the presence of a magnetic field. Now you might ask why it just attracts iron and all, it won't attract wood, right? That is its property. That is how a magnet works. So we know magnet has two poles. Which poles are they? We know they have our bar magnet has a north pole and a south pole. The end of the magnet that points towards the north of our earth is called north seeking. Well, original name is north seeking pole because the compass needle tries to seek where the north of the earth is, but it's called north pole, and the end that points towards the earth's south is called our south pole. And we know that if this is my magnet, okay, if I break this magnet, it won't be like this, that one side of the magnet will be north. If I break this, it won't happen that this is now north and this is now south. No, this won't happen, right? We all know that. If I break this bar magnet into two bar magnets, two poles will be formed, north, south, north, south. Correct? Very good. So moving on to the next one. Also we know that north and north pole will repel each other. North and south pole will attract each other. Hence, like poles attract, unlike poles repel. Moving on to magnetic field. So you have Bluetooth headphones, right? All of you have. If you move a certain distance away from your laptop or your phone while your Bluetooths are connected, they will stop responding to your phone, right? They will stop connecting. Your music will stop playing. Your lecture will stop playing. Similarly, it is the same case with the magnet. If you move you have iron and you have a bar magnet, they are getting attracted, they are sticking together. If you move that iron far away, let's say 10 meters away from this small chotu magnet, of course it won't repel the iron anymore. Why was iron being repelled? Because due to that magnet, in the surrounding area, a magnetic field was being produced. Because of this magnet, by this magnet, a magnetic field was produced which was attracting the iron fillings, and if you take the iron fillings a certain distance away from the magnet, it won't repel because it is out of its magnetic field area now. So the region around a magnet or a current carrying conductor. Because why it's mentioning current carrying conductor? Because we just studied what Oyster G said, that sir said that if you pass a current through a conductor, it will get magnetized. That's what we studied, right? So if current carrying conductor, there is a certain region around a magnet or a current carrying conductor in which the magnetic influence can be felt, or within which a magnetic force can be experienced. We know that the unit of magnetic field was kept on the name of Tesla G, our very own Nikola Tesla scientist. Now, because of this magnetic field lines, we came up with the fact that we can't see this magnetic field, right? But we thought of some imaginary lines which are called magnetic field lines, which are imaginary lines that represent in which direction the magnetic field is present. Okay, the strength of magnetic field also it represents, that we'll study in the coming slides. Now, this is a very important slide. Take care of everything that is mentioned in this. Everything should be precise according to this slide, because one word here and there will create a problem. So we know that the North Pole and South Pole outside the magnet form closed loops. So we are studying about the magnetic field lines. Now what magnetic field lines says is, see, this is, if this is my bar magnet, what did we study? North and south. What it is saying is, the magnetic field lines outside the magnet, what? Outside the magnet, it will travel from north to south, travel from north to south. Inside the magnet, it will be south to north. Outside, north to south. Inside, south to north. And similarly for other ones. Okay, all of them will travel north to south, south to north. Similarly above, north to south, south to north inside the magnet. Okay, the first point is proved. The second point says, the closer the magnetic lines are, what? The closer the magnetic lines are, stronger will be the magnetic field. But if the magnetic field lines are far away, it will be a weak magnetic field. Third point says that the direction, that this is our magnetic field line. Okay, it is going from north to south, and inside it's going from south to north. If I want to see the direction of my magnetic field at this particular point, so what I will do is, I'll just at this point I'll draw a tangent. I'll draw a tangent to this magnetic field line, and that will be the direction of magnetic field, my friend. So at this there will be one tangent. Now this also says, this also says one more thing, that magnetic field lines can never intersect. Why, ma'am? Why cannot they intersect? Because if they intersected at one point only, we'll have two tangents. Okay, in the direction of field lines we'll have two tangents at one point, and by mathematics we know that we can't have two tangents at one point. Very good. How much time it is? 8 minutes. Okay, next. So we drew the magnetic field lines for a bar magnet, and let's hold on this for a moment for a straight wire. We'll see this in just a minute. Okay, just a simple question. This is a very important question. It has been asked in the paper lots of times. Why do two magnetic field lines never intersect with each other? If two magnetic field lines intersect at a point, then there will be two tangents at that point, and hence magnetic field will have two different directions. Magnetic field will have two different directions at one single point, which is not possible. Okay, moving on to the next one. Now we are going to study magnetic field. We have studied magnetic field for just a general case. Okay, let's study magnetic field for a current carrying conductor. So when a current is passed through a conductor, what happens? When a current passes through a conductor, magnetic field gets generated, and we know that magnetic field as represented by us using magnetic field lines. This magnetic field due to current carrying conductor, we will study some properties of it. So we took a circuit Okay, we created a circuit. There is a key, there is this compass we kept one battery on it. Okay, so what we did is we kept a straight wire inside that circuit and we placed a compass directly over that wire or parallel to that wire. So what we saw is that, of course, we saw that when we pass the current through that circuit, this compass will get, the needle will get deflected. But we also saw that if we change the direction of the current, what do I mean by change the direction of current? Like right now, the direction of current is like this, okay? So the needle is pointing towards this side, okay? But if I change the direction of current, now my direction of current is opposite. Okay, there is some problem. This will be negative, positive, and this is negative. Okay, so the direction of current is like this now. If the direction of current is like this, so if I switch the position of this battery, if I switch the ends of this battery, the positive negative gets switched, the direction of current will get reversed, and if the direction of current gets reversed, the compass needle now shifts in the opposite direction. It shifts in the opposite direction, hence saying that direction of current also impacts the direction of our magnetic field, which is a very important point. Next, now we'll see some specific conductors. First, let's see the magnetic field due to a current carrying through a straight conductor. We just take this, nothing, we'll just take a straight wire. Okay, we'll just take a straight wire. Now let's say this is my straight wire. What I do is I connect a whole circuit, a key, resistance, and a battery and emitter, everything, and I place a piece of cardboard, let's say a paper, perpendicular to that wire. Okay, when I pass the current, what I do is I sprinkle some iron fillings over this paper. Then I see what is happening. Due to this, their iron fillings are taking the shape of concentric circles like this. The iron fillings get scattered around on that paper in the shape of concentric circles. What is concentric circle? The circles which have one center but different radius. All these circles have one center but the radius is different. Correct? So we have just battery, resistance, and a long straight thick wire. Connect this with copper and all. The main point here is that the straight wire, the straight conductor, has magnetic field lines in concentric circles around it. Okay, good, very good. Now, we also need to study the factors affecting. This is a very important topic. The factors affecting the magnetic field. These magnetic field, what are the factors that are affected by this? So we know that magnetic field strength is directly proportional to the current. The more heavier the battery will be, the more current there will be in the circuit, and hence the magnetic field will be strong. Now, as I said in the Bluetooth, if I move away from the laptop, the Bluetooth connectivity gets decreased. Similarly, as I move away from the center, from this wire, my magnetic field strength will get reduced, will decrease, and hence it is inversely proportional to the distance. Now, change in direction, we also studied this. Change in direction of current changes the direction of magnetic field, and it does not affect the magnitude of the our magnetic field, but it switches the polarity, it affects the direction of the magnetic field. Now, we'll see now the magnetic field in a circular route, but before that there is a concept, again very important. This whole chapter is important, but let's take it bit by bit. Okay, right hand thumb rule. There is nothing literally in this. There is a straight wire that we studied. What we'll do is, this is a straight wire. We'll hold this straight wire in our hand, and our thumb will point in the direction of current. Now, my thumb is pointing in the direction of current, and I'll curl my fingers. The direction in which my fingers are being curled is the direction of magnetic field. They are coming outwards, so they are coming like this. Okay, if I hold this wire in, the current is in downward direction, then the way my fingers will curl, they are curving inwards. So in that case, my direction of the magnetic field will be inwards. What do we have to do? We have to hold the wire and point the thumb in direction of current, and curl the fingers will give the direction of magnetic field. As simple as that. Okay, let's use it to find the magnetic field through a circular loop. So here, let's say this is a circular loop I have, and I have to find the direction of magnetic field or the magnetic field around it. So what I'll do is I'll take this small portion. Let's take this small portion of this big circular loop, and if I zoom in completely, it will if I see it, it will appear to me that it's just a straight line. When you come to college, when you go to your school, you travel on earth. We know earth is round, but when we travel, we don't travel like this, right? We don't climb up and then go down. We don't do that because the earth curvature is very big, and when the curvature is very big, we don't seem to notice that the curvature is round. It appears to us that it's plane. Similarly, if I zoom in, the curvature will appear to me as straight only. So now the current is going upwards, let's say. Okay, in here what it is, the current is clockwise. The current is clockwise. Okay, what I'm doing is I'm holding with my right hand, I'm holding the pen or this wire in my right hand. So current is upwards. I held the wire in my right hand. When I curl around this wire, this is the way it will form line. So it's coming outwards and then going inwards. Okay, when I hold the wire in my right hand, point in the direction of current with my thumb and curl the fingers, it will give me the direction of magnetic field. And in this particular, I'm holding the current is upwards, so I'm holding it like this. It's coming out from here, going in, coming out from here, going inside. So this is how, if I make so many at so point, this is coming out, going in, coming out, going in, coming out, going in. So the inward of this circular loop, the inside of this circular loop, the magnetic field is in inward direction. Understood? So we can just cram it in our mind. So this in both, you should know all these concepts by heart, and to just cram it, we'll use this certain trick. Not a trick, we'll just remember that if my current is clockwise, the field will be inwards. The field will be inwards. If my current is anti-clockwise, how? Current is downwards. Current is downwards. If I curl my fingers, so it's going in from this side and coming out from the inside. So inside, the magnetic fields will appear to come out. The magnetic field will be towards outwards. So for clockwise, magnetic field inside the circular loop is inwards. For anti-clockwise, magnetic field inside the circular loop is outwards. Very good. We're done with two of the conductors. So again, we have to study the factors affecting the magnetic field in a current carrying circular loop. So again, if current increases, magnetic field increases. That is like short. If the current increases, magnetic field increases. If you don't know this, you should seriously think about. Now, we studied one by distance. As the distance increases, the magnetic field decreases. Okay, distance increases, magnetic field decreases. Same, if the radius of the loop increases, if we go far away from the loop, the magnetic field will decrease. Again, this is inversely proportional to the radius of loop. Okay, then the final point is this loop. If you go away from radius of loop, if the radius of loop increases, the magnetic field decreases, and if you move away from this particular loop, the magnetic field will also decrease. Oof. Okay, next one is magnetic field due to current as well. There is a short one question that is definitely will come in your boards from solenoid. It's a really important topic, really easy, not much to be worried about, but it's very important. So ma'am, what is solenoid? Solenoid, we study about a circular loop. So if you connect lots of circular loops together, then that structure is just called solenoid. But that circular loop should be of insulated copper wire. This is very important. See, that's why I highlighted it. This is very important. In solenoid, the wires, the circular loops should be insulated, should be made up of insulated copper wire, and they should be wrapped very closely in the shape. And when I wrap it around, it will become a cylinder. Okay, so this, see, this, they are wrapped around in the shape of a cylinder. Got it? Understood? A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Now let's see something. If this is my positive, obviously we will connect it with a battery and a key. If the positive end, if the wire is connected to the positive end, then that end of solenoid will become a south pole. You will study this in your PU1, PU2 classes, so no need to worry why the positive ends become south pole and all. You just need to see that the positive, the end of the wire which is connected with the positive end of the battery, that part of the solenoid will become a south pole, and the negative one will become the north pole. Okay, the negative one will become the north pole. And we studied for a bar magnet, what happens? The magnetic field lines always travels from north to south outwards the magnet, and south to north inside the magnet. Can you see all the rays, all the magnetic field lines are traveling inside from south, coming out from the north, and they are again going back in the from the south pole. So outside the magnet, north to south, inside the magnet, south to north, just like a bar magnet. So a solenoid is vaguely comparable to the bar magnet. So when you wrap insulated copper wire in a closed loops in the shape of a cylinder connected with a battery, run current through it, it behaves as a bar magnet. How interesting that is. Okay, now a very important point, this is a very important point to keep in mind. Like, see, outside the magnet, the field lines will get away. Okay, it will get away. So this field is not uniform, right? So here they will closely packed, and as we go away from the solenoid, the field lines are getting separated by a larger distance. So outside the magnet, the magnetic field is non-uniform. So in overall, inside plus outside, the magnetic field will be non-uniform. Oof. But inside the magnetic field, see, inside the magnet all rays are equally placed or passing at an equal distance. When they are passing equally from an area, what is it? That is a uniform magnetic field. So inside the solenoid, the magnetic field is uniform. Very good. We have completed magnetic field of a straight conductor, a circular loop, and a solenoid in how many minutes? I can't see. 24 minutes. Okay. Let's go. Next is factors affecting this magnetic field. Again, if the current of solenoid increases, magnetic field increases. It also increases. If you increase this number of turns, magnetic field will also increase. This is wrong. So magnetic field is inversely proportional to the distance. As you go away from the solenoid, magnetic field strength decreases and not increases. It decreases. What did I just write? Okay. Next one is electromagnet. So we just studied our solenoid. If I keep a soft iron core, I have a solenoid. If I keep, these are the wires wrapped around. If I keep a soft iron core inside my solenoid and pass current through it, we saw that when that current was passed and that soft iron core became a magnet. If you place a soft iron core, wrap a thick copper insulated wire around it, pass current through it, that soft iron core becomes a temporary magnet. Why temporary? Because as you stop the current, it will again go back to its original configuration. So a strong magnetic field produced inside a solenoid can be used to magnetize. What did we do? We magnetized a piece of material which was not a magnet before. Okay, a magnetic material like soft iron core which was placed inside the coil. So this magnet that was formed, this soft iron core which converted into the temporary magnet, is called an electromagnet, and it's a temporary magnet. Okay, next, it's just a difference between permanent magnet and electromagnetic. Permanent magnet is permanent. If we stop or pass the current through it, it won't affect the magneticity of this. If electromagnet, if we stop the current, it will not be a magnet anymore. This magnet has fixed strength, but if we increase the strength of the battery for electromagnet, its strength, magnetic strength, will increase, and it has fixed polarity, but it has variable polarity. What does that mean? The one we studied. If I switch the battery from this to this, the direction of magnetic field in a solenoid will also switch. So that means it has variable polarity. Moving on, now we studied what magnetic field did, how magnetic field lines appear, what is the direction of magnetic field, what are the factors that are affecting our magnetic field. Next, we are going to study force. Because this current is producing magnetic field, this magnetic field will produce a force. Now we are going to study force on a conductor, current carrying conductor in a magnetic field. So what we did is, we took a aluminium rod. We took a aluminium rod, this, and we hung it in between a horseshoe magnet, and we tied it with a battery. As we pass the current, this aluminium, obviously the current goes into the aluminium, and it kind of becomes it behaves as like displaces from its position and behaves as a magnet, and now this is produced inside a magnet. So what happens is, this current carrying conductor, the current carrying conductor, which is our aluminium rod, it experiences a force whenever it is kept in an external magnetic field. We took an aluminium wire, connected it with the we connected it with a wire, with a battery, and as we passed current through it, and we kept it in near a magnetic field. So as the current was passed inside that conductor, inside that aluminium rod, the magnetic field would be produced. It will experience a force only when it is placed in a magnetic field. Okay. The direction of this force again can be reversed if I switch the polarity of the battery, and if I switch the direction of current. And the examples of these are just electric motor, generator, loudspeakers, microphones, and others. So moving on, oh, this is very important, Fleming's left hand rule. Now, very important but very easy. Left hand rule, this is my left hand. If my index finger is pointing in the direction of magnetic field, my middle finger is pointing in the direction of current, then what we are studying force. We need to see the direction of the force. Then my thumb will point in the direction of force which was experienced by that particle because of that current and magnetic field. What we're doing, stretch the middle finger, index finger, and thumb of your left hand. Remember this is important part. Left hand, don't use your right hand for these such kind of things. Don't mix up, confuse your hands. Fleming's left hand rule. Thumb pointing in the direction of force, index finger pointing in the direction of magnetic field, middle finger pointing in the direction of current. Let's say I have a magnetic field in this direction and my current is downwards. So they ask me what will be the direction of force. What I'll do is, I'll just point my index finger in the direction of magnetic field, my middle finger in the direction of current. So this is current, this is magnetic field, and my thumb will give the direction of force, and here it is outwards from the board. So for outwards we use dot. So the force in this situation will be outwards. Force will be outwards. Thus we did Fleming's left hand rule in just 2 minutes. Okay. What is this? This is not the heading. This is our household circuit. And of course now we know that we use so many wires in our households. We use fan, all these boards I'm using, so these are getting some So these boards that I'm using these lights and all these AC, these all are using some kind of wires in our households, right? So those kind of wires, what are those three kind of wires we use in our household? First is red wire, black wire, green wire. The red wire is also called the live wire. It is of positive charge, so it carries the electric current from our electric pole to our homes. Neutral wire does not carry any kind of electric current or something, but it completes the circuit and takes back the excessive charge back to its source, that is, let's say, our electric pole. And green wire, it is very important. Why? Because it protects us from getting shocked. Why? How? When you see you have metal bodies of some cooler, you might not know cooler in these days, but back in the days the coolers have metallic body, and if the current is getting leaked through the metallic body, if you touch that metallic body, it will get you will get shocked, you will experience a current, and we don't want that. That is dangerous. So what it does is it connects the electrical appliance metal case to the earth. What we do is we pass the wire and we connect it from the metal body and take it inside the wire, inside the earth, and earth absorbs all the extra charge, and hence we do not get shocked. Moving on, there are two types of currents that we studied: AC, alternate current; DC, direct current. In our households we use alternate current, but in my mic, if I'm using direct current. In alternate current, the magnitude switches positive negative, positive cycle, negative cycle. But in DC, the electric supply of the current remains constant, it does not vary, so it changes its direction periodically, but this it has fixed direction. Then it has also changed its magnitude. Now 0, then 1, then 2, then highest, then coming back 0 again, so its magnitude is also changing. This has fixed magnitude. This we get household circuit. In household circuits we get AC supply. In our batteries, in our cells, we use direct current. In AC, for longer transmissions we use AC. Why? Because it has less power loss. DC, it has more power loss. Why it has less or more power loss, you will study in later classes. Next, this is just a question on Fleming left hand rule that I already told you. Electron enters a magnetic field at right angles to it. Now it is right angles to it as shown in the figure. The direction of the force acting on the electron will be. Okay, so Fleming's left hand rule, which is my left hand. So I'll point my index finger, middle finger and thumb in the perpendicular direction. Electron is going downwards, so current is upwards. If my current is upwards and my magnetic field is in this direction, so force is, this thumb is pointing inwards, this is pointing inwards. So what will be the answer? You comment down. I've told you everything. Now just comment down fast. Next, short circuit overloading. Every year one question has at least come from this topic in your 10th boards, not pre-boards or sample papers. 10th boards, every year one question comes from this. What is short circuit? And it's nothing. A short circuit happens when the live wire and neutral wire come into direct contact. We studied live wire, which carries the current in our houses. Neutral wire, which carries that current back to the source. It does not supply the current, but it carries just extra current. So if those wires, so what we do is we have these plugs, like these plugs in our houses. This is, let's say, positive, this is our neutral wire, and this is the green one that we earth. So we connect our device, let's say our mobile charger, in these two pins, right? These are pins, this is our charger. So in between these two pins we connected a resistance, so it doesn't have much higher current directly passing between neutral wire and positive wire. If I disconnect this charger and connect that red wire and black wire directly, do not do that. It's very, very, very dangerous. That will happen. That is when will happen short circuit. It means excess current passes through those wires, and it results in excessive charge, in excessive heating, and it can even cause fire, my friend. So do not do that in any case. Next is overloading. If I have socket, okay? If I connect multi-socket switch into that, and then I connect one more multi-socket switch into that, and then I'm using AC and my laptop and my phone charger, my Bluetooth, all in that, what will happen? It will get overload. It is not meant to give that much current to our appliances, and if we try to fetch that much current from it, it will get overload, okay? So it occurs when too many electrical appliances are connected in a single circuit, drawing more current than the circuit safe limit. That's what I said. Okay. This is the last topic, our household circuit. So what did I say? We get 3 wires. This one is live, this is a red wire, this one is neutral wire, this is a black wire, this is a earth wire, this is a green wire, this is a green wire, okay? Now this live wire carries the current. So we have connected this through this our electricity fuse. First we put a fuse, and what was the function of the fuse? To protect our appliances from excessive current, okay? We studied in the previous chapter, remember? So fuse, then we have our electricity meter. We all have electricity meters in our houses. Then this box contains, it's like a distribution on which each room has different, which room goes, which current goes to which room, which wires goes to which room, okay? So distribution box containing main switch and fuses for each of this circuit. Let's say this is room number 1. This is your room, your sister's room, and your papa mama's room. So when these wires are connected parallelly, what are they connected? Parallelly, so that each of them gets same voltage, that is 220 volts. Now see, all these wires are connected to these chotus, these ones, and this wire, the earth wire, is connected to the big upper hole in our socket. So the upper hole is for green wire, is for earthing, the lower 2 holes was for positive wire as well as for neutral wire. See, this neutral wire is getting connected to this hole, and this positive wire, this red wire, is being connected to this hole, and the upper hole was for green wire, which is earthing. Okay, so we are done with our rapid revision. I hope, I don't know what time it exceeded. It was good. Now we have also started a 5-minute 5-mark series where we'll teach you concept, PYQ and solution in just 5 minutes. So go join our WhatsApp channel. You will get all the notifications and everything, and we study and we teach completely in English, because you have to write your CBSE exams in English only, bacha. So go join our WhatsApp channel. You will get proper notifications so that you don't miss any class, so as to ace your 10th boards. Also, I request, if you liked this video, give a like, subscribe the channel. We are trying very hard, we are working very hard to make you ace your board exams, which is a very good feeling. And so subscribe our channel, sirs, and hit the notification button so that you don't miss any video. And study hard, but enjoy your festivals as well. Tata, bye bye.